So we've set up now our critical point definition, what exactly will qualify as a local max or min, what a saddle point is, and then how do we classify these points based on the second derivative test. Okay. So again, our ultimate goal is to be able to find a max or min of a function, because again, in statistics, we're often doing that. We're often finding the max or mins and maximum likelihood estimation. In least squares regression, finding those like beta hats, those coefficients, finding a lot of times you're just given the equation, you're just going off the equation, but coming up with those equations is a matter of a maximization problem. So it's used everywhere. So we want to be able to handle all types of different cases here. So first we're focusing on just the points where the partial derivatives are equal to 0. So we're going to use the second derivative test here to classify points as either saddle points or local maxes or mins, or maybe neither, if that is one of them that comes out here. So we had this function before, and we found the critical point to be -1, -1. This was about 2 videos ago at this point. And we looked at the graph, and I mentioned that it looks like it's a saddle point because we could see kind of that it wasn't there was a dip in the graph, but it was close to the points that were going downwards. So it looked like, it looked like a saddle. It had that shape of a saddle. Okay, so I would expect this to be a saddle point. So let's go ahead and do the rest of the math here. So we already had these, so I'll just write them down quickly again here. We're going to need the second derivatives this time, though. We're going to need all of the second derivatives this time. So that's going to be 2x minus 8y minus 6. Okay. And we set these equal to 0 and solved. That's how we got the -1, -1 critical point. Okay. Second derivative with respect to x again is going to be 2, and that's it actually. Fyy is going to be -8. I'll just do this one over here. Fxy, doesn't matter which one we do this with because they should be the same, right? But if we take this one with respect to y now, we'll get 2. And if we did this one with respect to x, we'd also get 2. So we see that they're the same here. So the functions, they actually come out pretty nicely here because they're all just constants. So with that d quantity, the discriminant, we need to plug in the point, the critical point. But here they're all just constants, so we don't even have to worry about that. But know that we are going to need to do that if we actually have x's and y's in here. We would plug in the critical point. Okay. So that d quantity is going to be fxx, which is 2, times fyy, which is -8, minus this one squared. Okay, so -16 minus 4 is going to give us -20. So here d is less than 0, so this implies that -1, -1 is a saddle point. Okay. And then we're done there. So there's nothing left to do once we determine that it's a saddle point. So this tells us that we do not have a local max or min on this function at all, because that was the only possible place to have a local max or min. So there's no point to even consider here. We could have an absolute max or min if we had a closed set. If we were looking at like just some like disk, right? We could consider the boundary points and maybe we would have an absolute max or min, maybe. But on the entire domain, because this domain is all real numbers, we're not going to have any absolute max or min either. Okay, so that's the same as when we did it in single variable calculus. I don't want to do the other example we did yet because that one's a lot more complicated with the square root in there and with that boundary. So the second derivative test doesn't give us any ways to handle the points that where the derivative doesn't exist. So we won't look at those ones yet. So let's just look at some other ones here. Okay, so let's look at 4x squared plus 9y squared plus 8x minus 36y plus 24. Okay. So this second derivative test is going to be used mostly for well-behaved polynomial kind of functions like this one, right? Mostly because we need continuous second partial derivatives in order to even apply it in the first place. So fx is going to be 8x plus 8. And we'll set that equal to 0. Fy is going to be 18y minus 36. Set that equal to 0. So this is going to imply x is equal to -1. This will imply that y is equal to 2, right? So this is going to be -1, 2 here for the critical point. And let's see if we actually need to plug it in. It looks like we won't because we're going to get constant functions again here. So we'll definitely do one where we don't just get constant functions. Okay, so fyy will be 18, and then fxy is just going to be 0 actually. So d is going to be 8 times 18 minus 0 squared. So that's what, 144? I'm not sure. Hopefully that's right, but it doesn't really matter if it's right because ultimately we know it's positive. You don't even really need to do the calculation there. We know it's positive, so that means that there is a local max or min here. So now we need to determine if it is a max or a min, right? And that's going to depend on the sign of xx, this one. Here we see that it's positive, so this implies that it is a local min. Okay, so going back to the little chart I made here, right? D is greater than 0, so then you look for it, which one is fxx. Fxx is greater than 0, so therefore it's a min. So D is greater than 0, fxx is greater than 0, so what's the point? -1, 2. So there is a local min at -1, 2. Okay. Let's go ahead and look at this point graphically. Okay. So here we go. So here is the function. So I had to zoom out quite a bit so that we could actually see the bottom of this. But we can see right here, it's kind of hard to tell that it's even at -1, 2. You know, it really doesn't look like it's lined up with it at all. But we can see that it's dipping down to -16, which is, I just put in the calculation here just so we can see that. So it's going down to -16. So that's what the local minimum value is at the point -1, 2. And this one does not at all look like a saddle point. So again, we can look at the one which did have a saddle point. So we can kind of see that now what the, maybe, you know, so this is the one we already looked at, but we can look at it again now that we know what a saddle point is exactly. XY plus 4. Okay. So again, we're looking at this point right here. So you can kind of zoom in and out to fill in different parts of the graph. Not that we need to, but just for some of these you will need to. Okay, so anyway, so we'll look at the negative, what was this one? -1, -1 here. So again, it kind of has that shape of like a saddle, right? Where it's going down on the sides here. So it kind of looks like a horse saddle. But again, that point, it's just it looks like, if anything, it looks like it would be a min, but it's not going to be the lowest point in any space around it here. Take any disk around that point, and there's going to be lower points than it. Sorry, I don't know why. I don't know how I changed the color there, but yeah. Okay, so let's look at some more examples here. So let's look at one that definitely will not come out to have a constant second partial derivative here. So f of xy is equal to x cubed plus 2xy minus 6x minus 4y squared. Okay. So we'll go ahead and take the first derivative with respect to x. 3x squared plus 2y minus 6. Then with respect to y, we get 2x minus 8y equals 0. Okay. So this one's going to be possibly a little bit harder to solve here because we do have that squared. So in this case, it's a little bit tricky. I think the quickest way would be to multiply this one by 4 and add them. But let's just go ahead and, yeah, I don't know. I think that would be probably the best way to do it. I don't have the answer for this one, so I'm just kind of looking at it on the fly here. Okay, so again, you can multiply these by like a constant and then add them together. So we do this with matrices all the time. This is called row operations. So, but you can do it outside of using matrices as well. So here, so that's going to be 12x squared. And remember, we can't add these terms, plus 2x. So we're looking to get a quadratic here. So the reason we do this is because then we get 8y minus 8y. Those go away. 4 times negative 6 is minus 24 equals 0. So 6x squared plus x minus 12 equals 0. So it's going to be harder and harder to avoid the quadratic formula. It's just going to come up a lot in, kind of naturally in problems like this. I don't know if you need the quadratic formula for this one, but you could probably can factor it. But just as an aside, it's probably a good time to learn the quadratic formula if you haven't already, because as I said, it's just going to get kind of harder to avoid in some of these optimization problems. So I'm just going to use a quadratic formula here. I'm not going to bother trying to factor it. So we have 1 minus 4 times 6 times negative 12. Okay, over 12. Okay, so 1 plus, ooh, that's a big one. That's going to be 288. So this is actually factorable because we do get a perfect square in there, because that's negative 1 plus or minus square root of 289, which is the square of 17. Okay. So this is going to be both negative 18 twelfths and 16 twelfths. Okay. And just to simplify, negative 9, well, actually, let's see. Take a 3 out of there. We have, we take a 6 out of there. So that's negative 3 halves. Yeah. And then this one's going to be, 4 thirds. Okay. So those are our x points. So we have 2 possible x points here, and then we can have the y point. So let's use this equation because it's just easier. 2x minus 8y equals 0. So if x is negative 3 halves, then that would imply that y, we're going to cancel these, add the 3 over. So y would be negative 3/8, right? Just want to make sure I didn't miss the sign up there. It looks okay. And then if x is 4/3, so that's going to be 8/3 minus y, or sorry, minus 8y. 8/3 minus 8y equals 0, which will imply that negative 8y equals negative 8/3, which would imply that y is equal to 1/3. Okay. So we have two critical points here. We have negative 3/2, negative 3/8, and 4/3, 1/3. Okay, so I'll make sure I didn't make any arithmetic errors here. Okay, I just checked them on Wolfram Alpha and it looks good. So we will proceed here. So we need to calculate D then. Okay, so I know this is getting a little bit cluttered here. So we found the first two partial derivatives, so we still need to find the second partial derivatives. So f(x)(x) is going to be 6x, and that's it. Okay. And then we need fyy, which is going to be negative 8, and fxy, which should just be 2, right? So then D is going to be, so we're going to need to do this twice, first of all, because we have two critical points, right? So let's do it for this one first. So we're going to need to plug the point in now because we actually have an x term in here. So 6 times negative 3/2 times negative 8 for the fyy part minus 2 squared for the mixed partial derivative. So this is going to be, what's that, negative 9 times negative 8 minus 4. So that's going to be positive 72 minus 4, 68. So greater than 0. So we're not looking at a saddle point. But then we need to determine the sign of f(x)(x), which is, when we plug the negative 3/2 in, it's going to be negative, right? So of negative 3/2, and then whatever the other point is, not that it actually matters for the sign, that's going to be negative 9, which is less than 0. So there is a local max at negative 3/2, negative 3/8. Okay. And now for the other point, we have 6 times 4/3 times negative 8 minus 2 squared. So this is going to be 8 times negative 8, so negative 64 minus 4, so negative 68 is less than 0. Okay. Just make sure. Yeah, that looks right. So because it's less than 0, that means that 4/3, was it 1/3? Is a saddle point. Okay, so it is neither a local max nor a local min.